Okay, pay attention.
Do we want to lower the lines?
Turn it off.
I think it's okay.
I'm just kidding. This is fine.
Okay. Well, whatever. Yeah, we're just going to be talking about what chassis subteam does. I know there's not a lot of communication between chassis and the electrical subteams, so hopefully this will give you a better idea of what we do. So first off, an introduction. I don't know if you guys know this, but we basically scrapped the design of the formula car that we were working on last semester. So this was what we worked on last semester. We designed a whole formula car, well, most of a formula car.
We're iterating.
We're iterating.
We didn't scrap it.
Yeah. But I mean, for a variety of reasons, we decided that we wanted to start a new design from the ground up. So this was last semester's, but we're sort of going to be talking about what we did last semester and sort of the key parts of a formula car and the process we take when we're designing things. So first, some of the subsystems. So this is just Delft's car. It's a really good European team, and I just highlighted some main things. These are the subsystems that we have on our formula car, sort of like the sub-teams we have underneath chassis. Under frame, basically we have the entire frame design. It's all about the structure, it's about mounting everything, a lot of system integration, and bringing everything together. And the pedal box, which is up there at the top, which is where your feet go. It has the brakes, the throttle. Super important because that's what makes the car go and not go. So we want to have a good one. Suspension is everything connected to the wheels, basically. We have A-arms, we have the wheels, knuckles, we have springs, which we call shocks, which are just what actually provide the suspension. Let the car go up and down, make the bouncy wagon actually bouncy. And then we also group steering into that because that's really integrated with suspension. And finally, we have transmission, which is in the back. We have our gearbox. We're not actually sure whether we're running a gearbox or a chain box or what kind of transmission we're running for the next formula car. But we're basically running motors with some sort of power connected to our wheels. And then for the current iteration of the formula car, we're planning on doing the battery boxes as side pods on the side of the car. So first, let's talk about the frame. James sort of touched on this last week, where there's a monocoque versus a space frame. Where a space frame is basically you have a bunch of steel tubes welded together into a big structure, and with a monocoque you have sheet metal molded into this nice pattern. You have carbon fiber laid up into something. And we decided to go with a space frame because it's a lot easier for us to manufacture. We don't have as much knowledge with working with composites, and we don't really have the tooling to work with sheet metal. So this was the space frame we designed last semester that Luke, Gordon, Brandon worked on. And there were some problems with it. It was pretty heavy, and we're still working on iterating on that. But it was a really good first attempt. It brought together all of our subsystems. It's really good. It's structural in the case of several impacts. For formula rules, basically, we have a bunch of load cases which we have to live by, which is if you hit something from the front, from the side, if you roll over, your frame needs to be able to take all of those impacts without injuring the driver. So one thing is the steel can't break, and also it can't deform enough that it goes in and crushes the driver inside the car. And that brings us to some of the tools that we use on Chassis Subteam, which is FEA. This is something you can do in SolidWorks. Basically, you can take your parts and apply fixtures to them, apply loads in different places. And you can see whether the parts are strong enough to take the loads that we expect, where they're going to fail first, whether they're going to fail or not. And this is a really useful part of Chassis Subteam. This is what helps us design parts to the appropriate level of overbuiltness versus not really structural enough. And also on the back here, on the top right, that's a monocoque car. I think it's Lund, which is some European team, which is pretty good. And on the bottom is OSU's space frame car. And you can see they both look pretty good. So space frames don't have to look ugly. That you might think just tubes might look pretty bad compared to a nice carbon fiber monocoque. But with body panels and good design, our car will still look pretty nice. So that's always important. Next, the pedal box. This is something Gordon worked on. The pedal box is super important, especially for you guys, because this is really integrated with sensing and powertrain. On one hand, we have the throttle, which is just connected to a pot, and this is what's going to drive the VDIF. This is something that's really important to pass over to sensing so that we know whether the throttle we're putting down is the same as what's getting output into the motors. And then on the other side, we have our brake pedal. And this is just a really brief picture of how brakes work, in case you guys are wondering. Basically, when you push down the pedal, you're compressing some sort of brake fluid in the master cylinder, which is that thing up in the top, and that pressure gets drawn through some brake lines and comes down into the brake calipers. And these just like sort of wrap around brake discs, which are giant spinning discs that spin with your wheels. And when you apply pressure from pushing down on the pedals, it just compresses and the friction slows down your car. So that's the REVO box. It's super important for everything. And then the suspension subsystem. Suspension is actually where maybe the bulk of the design of the car goes, just because it's so important, and there's so many components to consider. It's everything attached to the wheels. On the right, you can see our rear suspension from last semester, and on the left is our front suspension. The key difference, there's some extra linkages for steering in the front suspension, and you'll notice like there's this giant hole in the middle of the rear suspension, and that's for actually powering the rear wheels, because we need to be able to drive with them. But first, let's talk about what exactly suspension is, why it's important. Suspension is everything attached to the wheels. It moves up and down because we have shocks attached to it. And this is really important for vehicle dynamics. When you're turning, when you hit a bump, suspension is what makes sure that you keep traction as you're driving. It's what makes sure like the driver still has a smooth ride, but can also like feel the effects of the ground on the car, so that he knows like what he's doing, how the car is behaving, and it lets him have like a better feel when he's driving. We're running a double wishbone suspension, which is pretty conventional. You can see up at the top left, basically you have a wheel which is connected by two linkages to the main car. These are the two wishbones, control arms, A-arms, whatever you want to call them. And these form a 4-bar linkage. And basically as your car moves up and down, as it hits a bump, if it gets some air, the angle of the wheel will change as it moves up and down. And this gives rise to a lot of interesting behavior. There's a lot of suspension characteristics like camber, toe, caster. We're not really going to talk about them just because it'll take a really long time. But basically, like every angle between like every member on suspension gives rise to a whole bunch of really important vehicle dynamic behavior. And what we do is on the bottom, Audit was actually working on this, where we model all of our suspension in software we got from Lotus. And this helps us plot a whole bunch of graphs, which give us a good idea of what sort of behavior we're getting, and gives a good idea of how we're going to plan our vehicle and our suspension characteristics to handle like the on-road racing conditions that we expect to see. The other thing we do is push rod suspension. In the top left, you'll see the shock is just attached directly to the bottom A-arm, but this has a lot of problems. There's aerodynamics because like the shock is in the way of moving air, so there's some drag, and there's also additional unsprung weight. You want more weight to be like on the main body of the car, because this is going to be supported by the springs, and this gives rise to more consistent vehicle behavior, which is why we do what's on the top right, which is called a push rod suspension, where your shocks are mounted with the body of the car and then connected by like a smaller rod down to the wheel. And this makes sure the bulk of the weight is like with the main car and gives rise to like very consistent handling compared to normal suspension. And now I'm just going to go over the basic parts of suspension. These are the control arms. There's not really much to say about them. They're called like double wishbones, A-arms, control arms. It's basically what attaches the wheels to the main body of the car. They usually have like an A shape, hence the name. Not much to say about them, except on our last car we used aerofoil tubing, which is basically steel tubing with the profile of an aerofoil, which helps reduce drag and also makes it stronger in the case of front impact and weaker in the case of vertical loading. The knuckles are a really key hub of suspension mounting. These attach to the two A-arms. This is what the wheel and the hub attaches to. The brake disc and everything mounts off of that. The steering, this is where you attach your half shafts. In case you're wondering, it's like the giant gold piece in the middle of both of those. And this is like the main piece of the suspension. This is what connects everything. All of the tolerances on this, all of the geometry has to be really good in order to make sure that you're getting the proper vehicle characteristics. The one on the right is the front suspension, in case you're wondering, and on the left is the rear. And then there's the push rods and the bell cranks. These are just the shocks and the connections that attach to the shocks. Basically, we run these thin tubes up from the A-arms to the main body, and then these attach the shocks mounted along the chassis. On the right is an F1 car by Porsche, I think. Do you know, John? Maybe BMW. But yeah, a lot of nice cars use this, and it looks really good when it's well done, like over there. And then steering. This is what Alex and Michaela worked on. Steering is really important because we do this thing called Ackerman steering, which is something you can see on the bottom right. Basically, when you turn your wheels, your front two wheels aren't going to be parallel, because if they are, then they're not going to be steering around the same center point. If you guys worked on the sprint karts, like you probably heard all about this. This is another thing where geometry is really important, planning out your car. We use a rack and pinion, which basically turns the motion of your steering wheel into left and right motion. It's not too complicated, but again, it's really important for your subsystems. Working with VDIF especially, you want to take your steering wheel sensor and the motion of the wheels and combine that with the different power applied to the two motors in the gearbox in order to get really good turning. And then moving on to transmission, you get the gearbox. We're not sure if we're doing a gearbox or a chain box this time, but what we worked on last time was a dual motor gearbox, which you can see here. Two aluminum shells put together, a whole bunch of gears. You can see some stats down there. The reason we have this is because when you just buy your stock motor, they spin really fast, but they don't give you a lot of power. And that means you're not really going to move your car. You'll end up burning out your motor. It's not very good. So we geared down our motor to get extra torque and less speed. And this helps us accelerate better because you can actually push the car forward. But it also caps your top speed. So you want to have a balance between a high and a low gear ratio in order to still get that good speed and also some pretty good acceleration and torque. There's a few different types of transmission, which is what we're considering now for our new car. There's some fancy gears on the top left, chain on the top right, and belt on the bottom. And there are various advantages and disadvantages. When you're working with gears, for example, they tend to be a lot heavier just because you're working with like these big solid pieces of steel. Chain is nice because you can transmit power over longer distances, but it's less efficient than gears. And it also has a lot of benefits in the case of like impacts. If something goes wrong, you'll have a break in your chain, but chain is really easily replaced. Gears are expensive, and it's a lot harder to maintain if something goes wrong in them. And finally, on the bottom, we have belt. Belt is, I guess, even easier to maintain than chain because it's one piece. You don't have to like break your chain or do anything like that. But chain and belt ends up being the least efficient of the two. And then we have half shafts. Because you have suspension on a car, right, your wheels are moving up and down. You can't really run a solid rear axle, at least with the suspension setup that we have. So you need to be able to transmit power from the car to the wheels that's able to like flex up and down as your wheels are moving up and down. And this is where we use a CV joint, which is just like constant velocity joint. The ones we use are tripod housings, which you can see over here, which basically allows the entire shaft to bend up and down, but still transmit power. These get less efficient like as they bend up and down even more, but for the most part, they're really good at transmitting power across a variety of bump conditions. And then the half shafts, we're running carbon fiber half shafts, which just connect like the gearbox in the middle of the car to the rear wheels. And finally, the battery box. I'm sure you all know we're running Nissan Leaf batteries inside a battery box that we designed. In the previous car, we had a single large battery box, but we're thinking of splitting it up this semester for our second iteration because it's going to take up a lot less room, and we can put it on either side of the battery box, move the whole center of gravity forward on the car. We'll have additional wiring problems, but that's a powertrain's problem, not ours. So yeah, and that's it. You guys have any questions?
Come on, I know you all didn't understand all of that.
Can we go back to the steering wheel picture? I was just wondering, where would the steering wheel sensor be attached in this case?
Alex, you want to take that?
Yeah, so the steering wheel sensor would be attached at the bottom of this second part of the steering column, so closer to the rack and pinion than the U-joint in the middle. So that was actually one of the main reasons that we chose the ID for the steering column that we did. We're using aluminum tubing, and Michaela brought up the specs for it, the sensor that you sent her, and that was specifically designed for that. So.
I guess I'm just confused about where the outer part of the steering, like the part that has to be fixed of the steering wheel sensor, is going to be mounted.
Yeah, I think that we were talking about having mounts coming down from the frame and attaching to the steering column, and one of those mounts would be for the outer part of the sensor. And so, but the inner part would be mounted to the steering column, I think. Like, I don't remember exactly because it was before break, but I'm pretty sure. Yeah.
And then also in the pedal box, So I can't really see from this angle, but where will we be attaching the like potentiometers for determining where the position of the metal rocks?
Gordon, correct me if I'm wrong, but we're using
This
what
is
is
an old,
the potentiometers on the side.
yeah, this is an old design. We actually need to switch to a different type of potentiometer, or to a rotation sensor instead.
Okay. How will that be mounted?
Yeah, there's gonna be, a rod that's gonna slip over, and then, I think it has to be mounted on a PCB. Because the ones that were spec'd out earlier are, much too large to actually fit in the design. So,
And then for the breakover travel, that's a switch. So where is that going to be?
yeah, this design is completely changed since, although, and it might have, and then with this new car, you know, even the second version of this might be trash, so.
Iterated.
Iterative, yeah.
The second iteration of this might be trash. I mean, so like I've redesigned it since, I made that render
Mhm.
for the old design, so for the new iteration, it's probably gonna be completely different. But I imagine that it would be near the brake pedal, so I don't I can't answer that
Can you
question.
go back to the push rod / bell crank? What does it exactly push? Crank? Why are the names?
She's wondering.
So if we go here, basically you can see here there's the shock attached directly to the lower control arm, right? So basically, as this goes up, the whole shock will get compressed. But over here, when your suspension moves up and down, it's going to be pushing this little bar up. And then this is the bell crank, which rotates around this pivot. And as the push rod moves up, it'll move the bell crank over, which then compresses the shock, which is mounted along the chassis.
Okay.
But you can let it be mounted in different orientations.
Yes.
And you can also change, by changing the bell crank, you can change the characteristics of the springs.
So yeah, in the rear, we have like the two shocks mounted towards each other. In the front, we have them mounted along each other, along the body of the car. You can see here they do the same thing.
Any more questions? Ready for the quiz?
What happens if I fail?
Get
You're
kicked off the
kicked out.
team. I'm just kidding myself, quiz.
Drink some water, man.
Oh, is there a quiz?
I don't know, is there? I guess not.
No more questions?